All right, so what we're going to do is we're going to take that graph, the position versus time graph that looks like a cosine function, and relate it to this object spinning around and around. So what we're looking at here and what's important is not just the object spinning around, but essentially that which is the red object, but the blue object, which almost acts like its shadow. So if you were looking from the top of the screen and the bottom of the screen was a wall, right, and you were shining light, the red object, essentially that blue object is a shadow, and the shadow follows along back and forth. It gets faster as it goes through the middle of the circle and slower as it reaches the edges of the circle, the shadow that is. That shadow mimics the motion of the spring mass system. So, what we are going to do here is we're going to examine how we end up getting that cosine function. So, first and foremost, in this setup here, we have this object traveling from A to B. The light would be shining here, and on the wall, you would have the shadow of A right there. Sorry, that's a really, really weird shadow, but and then what we're just watching is as A goes around, as the object goes around in a circle on the turntable, we're watching the shadow on the wall go back and forth. It's essentially looking at the horizontal position of this as it goes around in a circle. So here, what are the assumptions in this scenario? We know that the object is traveling at a constant angular speed. And for one cycle, that is going to be 2 pi radians over the period. On the turntable here, this radius here is r, this is also r, and then the amplitude of this would be here to here, or on the other side, here to here. So if we look at the motion diagram here of the shadow, it will accelerate back and forth, getting fastest through the center, and the shadow would slow up on the sides, stop, and change direction. So when we look at this, using the amplitude and the angle, write an expression for the horizontal position. So we want to know the horizontal position as this object goes from A to B. So I want to know this horizontal location given the radius and the angle. So the best choice for this here would be cosine of theta is equal to x over r, or r cosine theta is equal to x. Well, we know that in the next part we can express this in terms of omega and t by making this substitution. Omega t is equal to theta by rearranging this expression here and placing this into the equation. So x r cosine theta omega t. And if we look carefully, the radius here is also the same distance as the amplitude. So I can substitute the radius with the amplitude. And then finally, we're looking at this for one complete cycle. So I can write this as a cosine 2 pi over t times little t is equal to my position, or the way it's written on your equation sheet, 2 pi times the frequency times time. And this is the equation for the graph you got in your lab, the position versus time graph of the object oscillating back and forth, the spring mass system in part 3. That is the equation for that cosine graph. So I'll be showing you how to use this later. And for now, you can find this on your equation sheet, and we'll discuss this in a few example problems later on.